Morning students. Today we shall discuss some definitions of rings like cancellation laws, integral domain, division ring, and then field. Division ring is nothing but a skew field. So, in which also we shall discuss before seeing the definition of division ring. We shall see some elementary properties of a ring. And what is the objective of this lecture is to understand the derivation of elementary properties of ring and also to understand the basic concepts or definitions of cancellation laws, integral domain, division ring or skew field, and field. Now let us see the elementary properties of a ring. So in which we have 4 elementary identities here. Let R be a ring, and for all A, B, C are the members of that ring. And now we shall see the first result. A dot 0 is 0 dot A is 0, where 0 is an additive identity. And second identity that is A of minus B equal to minus A into AB. That is also equal to minus A into B. And third relation is minus A into minus B is AB. And fourth one, A into B minus C is A dot B minus A dot C. First identity we shall prove here by taking that A dot 0 is A dot of 0 plus 0, since 0 is an additive identity. Just by taking 0 plus 0 here, there is no difference at all by adding this 0. And then by taking A dot 0 plus A dot 0 again by distributive law, and by taking, since 0 is an additive identity, by including 0 on the left hand side of that relation, which gives that A dot 0 this relation. By cancelling laws of that left cancellation law, so this A dot 0 and this A dot 0 gets cancelled each other, which gives A dot 0 is 0. And then now we should consider that 0 dot A equal to 0 dot 0 plus 0 dot A by adding 0 to this 0, since 0 is an additive identity, so that we shall write it like this. That implies 0 dot A is that 0 dot A plus 0 dot A. This is the right distributive law of that. And since 0 is an additive identity, so there is no difference at all by including 0 on the left hand side of this relation, so that then by make use of cancellation laws, so that gets 0 dot A and 0 dot A, which gives 0 dot A equal to 0. Then it implies hence A dot 0 equal to 0 dot A is 0, that always. And second property here in this here, A of minus B is equal to minus A into B, that equal to minus into AB. That since by taking the previous result that A dot 0 is 0, that, and by replacing 0 by B plus of minus B, in then which gives A dot of B plus of minus B is 0. That implies A dot B is plus A dot of minus B by left distributive law. This shows that A dot B is an additive inverse of A dot of minus B. That is, A dot of minus B is minus into A dot B. Now we shall consider 0 dot B is 0. So by again including that, this instead of 0 we can add it by A plus of minus A, so dot B is 0. and then by right distributive law, so that implies A dot B plus minus A dot B equal to 0. This shows that A dot B is the additive inverse of this A minus A dot B there. That is minus A into B equal to minus into AB there. That implies F minus B equal to minus A into B, that equal to minus into AB there. So this is the second property there. And third property, that minus A into minus B is AB itself. Now we shall prove this result, since by taking previous result, so that A into minus B is just by, since by minus taking previous result of this, just by taking minus into this here, just by taking that relation, and by taking this minus A outside of this B, so then minus into minus, since by taking A of minus B is minus into AB, that is what, if one is an unit of ring, that so that we can have to this here, and taking by this way, then we have seen this, so that we shall take that is what we have there, in particular that, because which is what we have that, which gives always AB there, because minus into minus that is result is clear. Particularly if I taking that is one is a member of R, unit element of R, so that by taking that is the instead of B or A minus 1, so that minus A, so that which gives that just by taking this side, so that which is what we have at this relation by a right distributive law, so that we shall write it this way, minus 1 plus 1 there. So this is what we have. So that is which shows that A is the additive inverse of minus 1 into A. Minus 1 into A is minus A itself. So fourth result is, as we know that it is the distributive property holds here, and A dot of minus B minus C is A dot B minus A dot C, that, so that we consider that left hand side of this result, and by taking this minus C can be taken this way, and by distributive law that we shall write it this way, A dot B plus A dot of minus C, that implies A dot minus C is minus AC, so that since by this result, so that we shall write it this way, so that hence we have A dot of minus B minus C is A dot B minus A dot C. And now we shall see the definition of cancellation law. What is the concept of cancellation laws? One is left cancellation law and the other one is right cancellation law. Any system, a ring R, is said to satisfy the left cancellation law if for all A, B, C are the members of R, such that wherein A is non-zero, AB equal to AC, that implies that by cancelling A by left cancellation laws, so that as you know that which is B equal to C, that this is what which is left cancellation law. Similarly, we can see that is the right cancellation law, since A is non-zero, B into A. Instead of writing A, B, we are writing BA, and instead of writing AC, we are writing CA. By this way which implies B equal to C, which way we can write it, that which is right cancellation law. So where that cancellation law fails, that, so that suppose if I take that is integer system with the members of 6 members in that set of integers, note that we have 2 can be taken in this way, 2 into 1, that equal to 2 into 4. Then which is what, but even though since 2 is non-zero, but 1 is never be equal to that 4. That's why it is this, in this case cancellation law fails that. And also we can take it matrices of ring, so that order 2, we know that 1 0 0 0 can be taken in this way, so that this system, but which gives this way, that However, everything works fine as long as there are not any non-zero divisors. Then only we shall this. And then we shall take another definition there. Integral domain. A commutative ring with unity without zero divisors is called an integral domain. And or else a commutative ring with unity element which contains at least two elements is an integral domain if it contains no proper zero divisors. That means, see that here, if you want to say that a ring R is said to be an integral domain if R has to be commutative, if R has an unity element, that R is also without zero divisors, then only we can say that it is an integral domain. Examples of integral domain are ring of integers is also an integral domain. Ring of numbers, it should be in the complex form, which is also an integral domain. A ring of numbers which is in the form of a plus root 2p, where a and b are integers, which is also integral domain. But ring of even integers with the zero is not an integral domain, since it does not contain unity element 1, such that a dot 1 equal to 1 dot a is a, though it does not have zero divisors. That's why it is ring of even integers is not an integral domain. See that commutative ring of complex number with unity is an integral domain. Now we shall see the definition of a division ring or skew field. A ring R is called division ring if all the non-zero elements of R has its multiplicative inverse in R. Means what? Which that R which forms a group means what? Which satisfy the four axioms of that, then only we can have. That is, each non-zero elements of R must contain a unit element. Then, or we note on this here, a ring R is said to be a division ring if R has at least two elements, then R has unity that, and each non-zero element of R has its multiplicative inverse, then only we can say that it is division ring. And now we shall see the definition, examples of a ring, division ring. Set of real numbers, set of rational numbers, set of complex numbers, which all are division rings. See that, but set of integers, which is not a division ring, because since as there does not exist multiplicative inverses, that's why ring of integers is not a division ring. So a ring of integers with the prime numbers, which is always skew field. So then also we have a unit element, that is where a is also real number. These are a this in this matrix is also division ring. And now last definition, a ring R is said to be a field if it has at least two elements, and this R is also commutative. This R has also unity then, and every non-zero element of that R has its multiplicative inverse. Means what? Ultimately, it is all these conditions as you have seen in the division ring, this holds that. In other way, we have seen that. So that or an algebraic structure F plus dot is said to be a field if this F plus is an abelian group. Means what? That is satisfied all the five axioms of an abelian group. And F star dot is an abelian group. Means what? F is non-zero. That system F, that structure is non-zero. That is an abelian group also then. And third condition, it is a distributive law also satisfied. Then this structure is called a field. That is a commutative division ring is said to be a field. Examples of a ring, this field are set of real numbers, set of rational numbers, set of complex numbers are field. But this here complex additive identity is 0, complex multiplicative identity is 1 in the complex number. and set of